Bismillahirrahmanirrahim. Today's presentation, the topic is drug distribution. Uh, as we know that drug distribution is the second parameter of pharmacokinetics, and pharmacokinetics is the movement of drug and subsequent alteration of the drug molecule within the body. So drug distribution, if we define drug distribution, it is a reversible transfer of the drug from one location to another within the body. So here in this definition, location means tissue. So and it is reversible. Reversible means that the drug after absorption is in the blood and it goes from the blood into the tissues and back into the blood, or it can go into another tissue afterwards. For example, this diagram illustrates the movement of the drug. The drug after absorption is in this chamber and it can go into the body tissue, or here, or it can come back into the blood, and then subsequently it can go for the metabolism. So if we talk about the patterns of distribution, it is the distribution of the drug is dependent on two factors: their lipophilicity and protein binding. We will come later on to these factors. So if we talk about the patterns of distribution, pattern means that how drugs can be distributed, whether within the plasma, the drug remains within the plasma, or drug may be uniformly divided into whole body or confined to one chamber. For example, if we describe body as the fluid compartment, blood is full of fluid. We already know from our physiology. So whether the if we define it like 1, 2, 3, 4 chambers. So if the drug remains within this chamber, this is a different pattern of the distribution. If drug is divided or distributes itself in whole of 4 chambers, then this is the different pattern. So if we discuss the patterns of drug distribution, drug confined to blood, it is high drug binding to plasma protein or larger molecular weight drugs will remain within the blood. So there are two factors which cause the drug to stay within the blood. Number one, high drug binding to plasma proteins and high molecular weight. So drugs cannot escape the blood. So where the drug will remain? Within the blood. So this is the first pattern. The second pattern is the low molecular water soluble compounds. They are uniformly distributes within the body water and then concentrate in a specific tissue, like here in this. The drug is distributed to a specific tissue, for example thyroid, bone, fat. There are certain drugs like iodine. Iodine, if given as a drug, for a tincture of iodine that is available in market, and it is used for thyrotoxicosis to neutralize. So that is uptaken by the thyroid tissue. There are certain drugs like, you can say tetracyclines. They are bound to bones, and barbiturates, they are distributed abundantly in fat tissue. So there are certain specific organs or tissues where the drugs have more affinity. So this is another pattern. So there is the fourth pattern is non-uniform distribution. Here, if you see, we can see this diagram as well. Here the 4 patterns of drug distribution here. This is number 1 here, and this is number 2. The drug is distributed in the interstitium, then extra and intracellular, then there is tissue binding. So here the example of tetracycline. Okay, then here the fluid compartments of the body. You can correct this. This is the fluid compartment of the body. Volumes of body fluids. If we talk about, this is the extracellular fluid is 14 liters. Plasma is 3 liter, while interstitial fluid is 11 liters. Intracellular fluid is around 28 liters. Total body water is 42 liters. So there are two types of factors. One affects the rate of distribution, other affects the extent of distribution. So the rate of distribution is how fast the distribution will occur. For example, if now at this moment the drug is present in the blood, and how fastly the drug will be distributed to a specific organ, that depends on membrane permeability and blood perfusion. Membrane permeability is how the membrane is, or how the location on which drug has to be transported. Blood perfusion is the amount of blood a tissue gets from the heart. So if we talk about membrane permeability, here we can see an example of that. Membrane permeability is here. You can see this is the blood-brain barrier. This is the CNS. Here, the continuous membrane. Here, the membrane is continuous, so the drug penetration is almost impossible. Only highly lipophilic drugs will cross these blood-brain barrier. This is the heart muscle. Here you can see this is invaginated, and then here this is the liver. Liver, you can see, is highly fenestrated, while pancreas is again can have certain drugs which can have a selected permeability. Then okay, membrane permeability is, again, you can see here, this is what we just saw is a sinusoidal capillary, liver, spleen, bone marrow. There are larger gaps. The structure of the capillary is made up of endothelial cell, and those endothelial cells are held by basement membrane, and there are large holes or pores within that basement membrane. These are called fenestrations or sinusoids. So this can cause easy transfer of the drug, or the even larger molecules can cross these membranes easily because of large. But on the other hand, blood-brain barrier, there is no fenestration. This is continuous. Here we have already seen it. So almost impossible for the smaller molecules to cross it. Only highly lipophilic drugs will cross these membranes. Then the second factor is blood perfusion rate. Blood perfusion rate is how fast. This is the percentage of cardiac output an organ gets. For example, brain, fat gets almost 2 to 4%, while brain gets almost 14 to 15%, while bones get 5%, heart gets 4%, kidneys get 22 to 24%. If you remember the flowing water example, the river, if river has a tributaries, the greater tributary will get greater share. Obviously, brain gets 14 to 15%, while kidneys get 22 to 24%. So greater portion of the drug will be distributed to the kidneys. Then factors that affect drug distribution: extent of distribution. Extent means how much drug will be distributed. Lipid solubility, as we just discussed about this. Blood-brain barrier is continuous and only highly lipophilic drugs will cross. So obviously lipid solubility will affect the ability of drug to bind to plasma protein and to cross lipid membrane barriers. So these drugs distribute themselves in two chambers mostly. Number one is the fat tissue, and they also can cross blood-brain barrier, and they can be distributed to CNS as well. So what is redistribution? Redistribution, as we just defined drug distribution as a reversible phenomenon. Drug can go into one tissue and can come back to the blood. So this is called redistribution. So effect of pH, I have highlighted this pKa. What is pKa? pKa, if you remember, we discussed in absorption, it is the pH of the medium at which 50% of the drug will be in ionized form and 50% will be in unionized form. So obviously pH will cause a significant difference in distribution of the drug. So the rate of movement of a drug out of circulation will depend on the degree of its ionization and therefore its pKa. So we discussed, if you remember, the acidic drugs will best absorb or will best distribute in acidic medium, while basic drugs best distribute themselves in a basic medium. So if blood becomes more acidic, if respiration is inadequate from the buffer system of the blood, if you remember, what is acidic or acidosis? Acidosis, if the blood pH drops down significantly from the normal towards the acidic side. And what is alkalosis? Alkalosis is the rise in blood pH than the normal. So if a drug is acidic in nature and alkalosis occurs, this will definitely, alkalosis is rising of the blood pH. So drug will become ionized in that medium, or vice versa. If acidic or acidosis has occurred and the drug is basic in nature, then it will become ionized, so it will affect the distribution. Then we have plasma protein binding. Plasma protein binding will cause more drug to stay in the central blood compartment. That's we already discussed. Plasma proteins are present in blood because these are negatively charged particles, and they are usually higher molecular weight. Usually the charge defines that the plasma proteins will not be filtered out of the junctions of the capillary, so they remain within the blood. So any drug that binds to plasma protein, that will remain within the blood. So that is the central compartment. Central compartment means, so in nutshell, if increased plasma protein binding, the decreased drug distribution will occur into the tissues. So changes in concentration, anything, any disease, any state that will cause, that has an influence on plasma proteins, the number of plasma proteins. For example, liver disease, old age, malnutrition. Malnutrition protein deficiency, because plasma proteins are made up of protein, and if a person is malnutrited, is deficient in proteins, lesser plasma protein will be formed, or liver disease, then this may result in significant higher level drug concentration. Free drug concentration will be greater. So tissue drug binding, already we discussed that certain drugs, for example chloroquine is a very hot drug nowadays in the liver, is due to the binding of the drug to DNA. It is almost 1000 times greater in quantity in liver as compared with plasma. So this is highly distributed to the liver, while barbiturates distribute extensively in adipose tissue because these are highly lipophilic or highly lipid soluble drugs. Tetracyclines bind to bone, this should be avoided in young children. So these were the factors and the drug distribution patterns. Then we have a volume of distribution. Volume of distribution is, if this is a hypothetical volume, or if we define volume of distribution, this is the hypothetical volume in which drug distributes itself within the body. So if you consider body as a fluid compartment, because we have fluid or we have water in many tissues, in many chambers. So if we, for example, here is the total plasma and extracellular fluid, intracellular fluid, all. So number one is the intracellular fluid, is all the water that our cells contain. If collectively we add up all that water, that becomes almost 28 liters. And if we add extracellular volume, extracellular means that it's outside of the cell. So it comprises of two chambers. Number one is the interstitial volume. Interstitium is between the cell and the blood vessel. Then it is almost 11 liters or 10 liters, while it is the plasma volume is 3 to 4 liters. It varies according to the person, and this volume is for 70 kg man. So what is volume of distribution? Volume of distribution is this is a hypothetical volume in which drug distributes itself. So volume of if the drug only distributes itself into the plasma, then the volume of distribution will be low. That will be only 4 liters. If drug distributes itself into interstitium or plasma, then the volume of distribution would be 14 liters. And if drug distributes itself into 42 whole body water, so that will be 42 liters. For example, ethanol, here this is ethanol distributes itself into whole of the body uniformly. So this is so volume of distribution tells us about how or which pattern, which we discussed earlier, which pattern a drug will follow. So for example, if we say I have a demonstration, how can we determine the volume of distribution, or VD? VD is, remember, VD is written as V capital and D in the subscript as a smaller. So this is called volume of distribution. So volume of distribution, for example, VD or the volume of distribution tells us about the half-life of the drug. Half-life means, for example, number one, I give you the example here. This is if the drug is distributed throughout the body, within the tissues, in the plasma and the interstitium, and into the cells. So it will take more time to get excreted because it will come it will be metabolized, it will come out of the cell into the interstitium, then into the kidney, then it will go out of the body. It will take more time. But if the drug confines itself or remains within the plasma, whole of the drug which you have administered, for example, you administered 100 mg, and 100 mg of the drug distributes itself in 4 liters within the plasma. It will take less time to go to the kidneys. While if 100 mg it distributes itself into 42 liters, then this will be more time it will take to get excreted. So half-life can be determined by VD, or VD can be determined by this formula. VD is equal to dose over plasma concentration. For example, if you administer 10 mg and plasma concentration is around 1 mg per liter from the graph, and VD is 10 mg over 1 mg per liter, and it is 10 liter. So the volume of distribution would be 10 liter. Here milligram will be cut down by the milligram, and then we have 10 liter. So volume of distribution is usually described in liter per kg. So other things that VD determines is where the drug is distributed. If the value of VD is small, then the drug mostly confines itself into the plasma. If the value or the calculated value of the VD is large, very large, since it is a hypothetical, so the value could be in thousands, which is not possible. So it means that the VD is large and the drug has distributed itself into tissues. Here is a demonstration for the VD. If you see here, first we start off with this. Dose is 100 mg. If this 100 mg is distributed in 1 liter, you see the color. If the same dose is distributed in 10 liter, you see it is more diluted. If the same 100 mg is distributed in 100 liters, it is more uniformly distributed, or you can see the color. Here is sorry for that. Okay, here again you can see the calculation of VD. VD is 5 liter. It is plasma. Plasma is 5 liter. VD is 5 liter. Concentration is plasma. 100 mg is the total administered dose, and concentration is 20 milligram per liter, and VD volume of distribution is 5 liter because it is confined to plasma. But if the drug is distributed to ECF, then you can see there is a drastic change in the concentration. Here is a 5 liter, and 10 liter the VD will be 15 liter. So if this drug distributes itself in intracellular fluid, the total, this is 45 liters for example. But if this drug has specific affinity for certain tissues, this can go up to 145, and if you add fat as well, then this becomes 1000, and 145 liter, then it becomes 1145 liters. So it means, so again we can see what I just told you. If the value of the VD is greater, for example this is 1145 liters, it means, mark my words, remember that if the value is higher, volume of distribution, then the drug distributes itself in two tissues. But if the value of the VD is lower, then it means it has involved only one organ, one compartment. For example, plasma. For example, ECF. So here you can see again, this is more beautiful description. This is the plasma. Plasma is running in vein. The blood plasma is running in vessels. So the volume of distribution is, or the drug concentrated in bloodstream. These are the patterns of distribution. Then you can see the coloration, and you can see here the drug in blood and extracellular. VD is changing. Drug equally distributed in blood and tissue. Here you can see. Then blood moderately concentrated in, and then usually it is out of. There is no drug in plasma, usually adipose tissue. The VD is 10,000. So here is. So thank you very much for your attention. We'll come back with metabolism in our next lecture. Any questions are welcome. You can ask in WhatsApp group.